to talk to you a little bit about the research we do under the title Dark Energy, Alchemy, and Quantum Teleportation, Science Fiction or Ph.D. Research. So just as a little bit of a spoiler, you're going to hear a lot more about Ph.D. research than science fiction today. But anyway, I work with Professor Dragan Hooder on research in theoretical cosmology, so I'm the dark energy part of the talk. But what my talk's really going to focus on is the cosmic microwave background, and I'm going to explain to you what it is and how we can use it to learn about physics, including learning about dark energy. So as a cosmologist, I'm required to show you this pie chart. So just to put things into a little bit of context, what it shows is the fraction of matter and mass and energy in the universe that's made up of different substances. And we've made this pie chart from, we get this picture from decades of observations of the universe on large scales. We see that only about 5% of the universe is made up of matter that we really know how to describe using fundamental physics. So this little 5% slice contains all the matter of the type we're familiar with. So basically anything that's made of atoms. That includes us, that includes the Earth, that includes the sun, and every star in every galaxy. That only makes up 5% of the matter and mass and energy in the universe. The rest of this pie chart has these somewhat mysterious sounding names, dark matter and dark energy. And these are things that we don't yet know how to describe on a fundamental level in terms of physics. So dark matter is, as far as we can tell, probably a type of particle that we haven't yet been able to detect directly. And we know that it interacts through gravity, but not with light. And we can study it by looking at how its gravitational pull affects visible matter that we can see. Dark energy, on the other hand, acts as if a sort of repulsive force, or sometimes we call it negative pressure, associated with empty space. And we study it by looking at how it influences the way the universe expands and behaves on very large scales. So the reason I want to talk about the cosmic microwave background, I'm hoping that by talking about a specific observable that we use to learn about these things, that we use to learn about dark matter and dark energy, I'm hoping that'll provide a sort of very concrete PhD research counterpoint to the maybe science fiction like mysteriousness that gets evoked when you say we don't know exactly what 95% of the universe is made of. Getting on to talking about the cosmic microwave background. The short description of what it is that it's light that we can detect from the early universe that we see coming from every direction on the sky in the microwave part of the electromagnetic spectrum. So by that I mean it's the same type of wave as visible light, but rather than having wavelengths on the order of micrometers or like the light that we can detect with our eyes, it has wavelengths of about on the order of centimeters. So when we detect it from every point in the sky, we do that using special telescopes that are sensitive to microwave. To get into some of the physics of how the CMB is produced, you need a little bit of background knowledge of cosmology, and it's all on this slide. So we need to know where this CMB comes from. Basically that the universe is expanding, and as it's been expanding over time, it's been cooling off. So if the universe is expanding and cooling over time, that means at earlier times it's going to be a lot hotter and denser than it is today. And the time that's relevant for when the CMB was created, and I keep referring to it as the CMB, that's just the acronym for Cosmic Microwave Background. The time that's relevant for when the CMB was created was when the universe was only about 300,000 years old. So that may seem like a long time, but to put that into perspective, the universe today is about 13.8 billion years old. So at 300,000 years, the universe was only about 1/40,000th of its current age. So if you were 1/40,000th of your current age, you'd only be a couple hours old. So this is a time when the universe was really in its infancy. At that time, the universe was hot, as we said, and it was the average temperature of the universe, the average temperature of stuff in outer space, was about 3,000 degrees Kelvin, or about 5,000 degrees Fahrenheit. So that's roughly the temperature of the outer layers of the sun. So you can imagine that if the average point in outer space is the same temperature as the sun, things are going to look kind of different. And one important way is that at those temperatures, it's too hot for stable atoms to be able to form. So any time that, say, a positively charged proton and a negatively charged electron might be attracted to each other through electromagnetic forces, And they normally want to try and stick together and form a neutral hydrogen atom. But at these high temperatures and high densities, any time that a proton and electron might try and stick together to form an atom, they'll pretty much immediately get hit by a high energy photon, so a high energy light particle, that will bust them apart. And so because of that, at this early time, instead of the charged particles being mostly combined into neutral atoms like they are today, the universe is full of this soup of separated charged particles, or a way to say that is it's ionized. So light interacts really strongly with charged particles. So a consequence of the universe being ionized is that it's actually opaque to light. Because light interacts strongly with those charged particles, a photon can't travel very, very far before it's going to bounce off of a charged particle. And so if you were to travel back in time to when the universe was only 300,000 years old and try to look through outer space, you wouldn't be able to see through it for the same reason we have trouble seeing through fog. So we can't see through fog because light bounces off of water droplets in the air, and so it can't travel in a straight line from where it's emitted to your eye. And so at this time, if you tried to look through space, the light would be bouncing off of all these charged particles, so you couldn't see through space. Several thousand degrees, I think you'd have bigger problems if you were to travel back to that time. But anyway, so the universe is opaque and it's ionized at the when the universe is only 300,000 years old. But remember, I said that over time the universe is expanding and cooling. And eventually it's going to cool enough so that those protons and electrons can combine to form neutral hydrogen. When that happens, those photons, which had been bouncing around like crazy off of all of these charged particles, they suddenly have nothing to bounce off of and can just fly freely through space. So space becomes transparent. And it's that light that's released when the universe first cools enough to allow atoms to form. We observe that light as the cosmic microwave background. And we can detect it, as I said earlier, using special telescopes. So what I'm showing on this slide is sort of the latest and greatest map of the cosmic microwave background that was made using the Planck satellite, which is pictured in the lower right-hand side of this picture. And this map shows data collected about the cosmic microwave background that was released just earlier this year. So by looking at the set of wavelengths of the cosmic microwave background photons, the Planck satellite we can infer a temperature from the temperature of the stuff that those photons were emitted from. And what this map shows is small fluctuations in temperature observed on the sky. And I should say, what this plot is showing, or this map is showing, is just a map of the whole sky looking out. It's projected on the screen the same way that you would project a map of the world from a globe onto a wall map. So we have a similar map on this beach ball here, which would be sort of flattened out to be the map on the screen. But yeah, so the different colors represent different temperatures, where the red spots are places on the sky where the CMB light is slightly hotter than average, where the blue spots are slightly colder than average. And it's really by studying these fluctuations that we can get a lot of physics information out of this kind of map. We know how to describe the physics of the early ionized universe pretty well, and from that we can just understand that at early times, the fluctuations in temperature their properties are governed by oscillations that took place at early times while the universe was ionized that have to do with the competing forces of gravity and pressure. So I tried to illustrate this in this little cartoon on the right here. And what this is meant to show is an overdensity in the early universe. So a location in space where there's slightly more matter than average. Now, because gravity causes mass to attract mass, gravity is going to pull nearby matter in towards this overdensity because there's slightly more mass at this place than average. So for dark matter, which if you'll remember interacts through gravity but doesn't interact with light, dark matter will just feel that gravity and will get pulled in towards the overdensity and clump up. And I've tried to illustrate that using these gray clouds. Things work a little bit differently for the charged particles and these photons. Remember that they're really interacting and all bouncing off of each other a lot. The photons and charged particles will get pulled in towards the overdensity. But as they get pulled in, they'll also get compressed. And those photons are going to heat up and provide a radiation pressure, provide an outward pressure to counteract that compression. So you end up getting the charged particles and photons going through these oscillations where they get pulled in through gravity and pushed out by pressure over and over again, essentially, until the universe cools enough to release that light as the CMB. So when we look at a map like I showed you on the previous slide of temperature fluctuations on the sky, what we're seeing is a snapshot of what these pressure gravity oscillations were doing at the moment that the universe became neutral. And I want to talk more about how we get physics information out of that. And to do that, I'm going to sidestep a little bit and talk about a little bit more, maybe a slightly more familiar kind of pressure wave, our sound waves. So specifically these sound waves. So what that sound is the sound of the third string on a guitar being plucked, so it's a G note. And let's just think for a second of what happens when we pluck a guitar string. We pluck the guitar, and the string and, I guess, the body of the guitar are going to vibrate, and they're going to push the nearby air molecules back and forth and cause fluctuations in the air pressure near the guitar. Those fluctuations travel through the air as sound waves, so pressure waves, and until they get to, say, our ear where we detect them, or the microphone, which we use to record this guitar noise. You can represent the information about that sound wave in two different ways. First, you can just plot how the pressure near the microphone varies over time, and that's what this plot shows. So on the vertical axis, it shows amplitude, how much the air pressure near the microphone, or some quantity related to that the microphone detects, varies over time, and the horizontal axis just shows time. We can make another plot, another image of the same information if we, instead of plotting amplitude versus time, we decompose the sound into how different pitches contribute to it. And that's what a sound spectrum is, and that's what this image shows. So in this plot, the vertical axis is still amplitude of pressure fluctuation, still sort of the loudness of the sound, but the horizontal axis shows frequency. So frequency for sound waves corresponds to pitch, where a high frequency translates into a high-pitched sound. So on this plot, on the right-hand side, it shows how much high-pitched sounds contribute to the guitar noise, which I'll play again. And the left-hand side shows the contributions from low pitches. And we can see, looking at this frequency spectrum, that there's a big peak just under 200 hertz, and that's the frequency corresponding to this G note. So the sound that we hear for the note corresponds to sort of the main peak of the frequency spectrum. But we can see that the sound also has contributions from noise as well as overtones. And we can make and compare plots like this for any sound that we can record. So here, in the extent of my music recording career, we have the same guitar note as I showed you on the previous slide. And then the same note, the same G note, being played by plucking the low string on a violin. So we can hear those two sounds, and they are playing the same note, but they don't sound exactly the same. And the way that they don't sound exactly the same is really encoded in the fact that their frequency spectra look different. So if we look at these frequency plots on the right, these purple ones, we can see that because these two sounds are the same note, they both have a peak at just around 200 hertz. But the way that the contributions from the overtones and from the different pitches are a little bit different, and that encodes information about why a guitar sounds different from a violin, and that depends on both how the instrument is played as well as the properties of the instrument, so like what its shape is and what it's made of. And if you can guess what I'm getting at with this is that we can do the same kind of analysis with these fluctuations of the cosmic microwave background. So this is a little bit different because in that, instead of plotting pressure fluctuations versus time, we're looking at fluctuations in temperature on the sky, and instead of wavelength of a sound wave or frequency in time, we have to look at length scales on the sky. But this plot here, the wiggly plot, basically shows you the same thing as those sound spectra on the previous slide. The vertical axis shows you the amplitude of fluctuations, and the horizontal axis shows frequency, where the high frequencies on the right-hand side correspond to small length scales on the sky. And in the same way that a sound spectra contains information about the thing that made that sound, when we look at the frequency spectrum of the cosmic microwave background, we can learn a lot about the physics of the stuff that's participating in those early oscillations. So, for example, because dark matter and charged particles participate in those oscillations in different ways, we can actually look at the relative height of the different peaks in the sound spectra to learn about how much dark matter there is relative to charged particles. And because these fluctuations are actually caused by pressure waves at early times, you can convert them into a sound, and then if you multiply that sound's frequency by a huge number, so 10 with 24 zeros over it, you can actually convert it into a sound that we can hear. And I think this is kind of cool, so I'm going to play that for you. This was made by a professor at the University of Washington named John Kramer. Maybe, there it is. So you can hear that as that plays, it gets lower. And that's because between the time when the CMB photon, the universe first starts getting neutral, and when the last CMB photons are released, the universe is expanding, and so as it's expanding, the wavelength of that sound gets stretched out, so we hear the sound go down in pitch. So my research has to do with studying what the very low frequency end of this sound, the CMB spectrum. We're looking at the very large scales on the sky. And I work on trying to make sure we really understand, well, the different contributions to fluctuations on these scales. Specifically, I study this small secondary effect that happens to CMB photons between when they get released and when we detect them in our telescope. So on our way to us, these photons are going to travel through structures in the universe. So they might go through galaxies or groups of galaxies. And that'll actually change their energy slightly in a way that depends on how much dark energy there is. And that'll affect the CMB spectrum at these low frequencies. So I work on looking at, because this spectrum is affected by photons traveling through galaxies, I look at whether we can use maps of where galaxies are on the sky to disentangle what contributions to the CMB temperature fluctuations come from early times when the CMB was released, and which ones come from late times, which are from modifications of going through galaxies. And I do this by making simulations. So I'm proud to show these plots because I actually just got my code to make these earlier this week. So the top plot is a simulation of matter distribution on the sky, and the lower plot is a simulation of how that matter distribution would modify the CMB temperature fluctuation. So it's by using these simulations that I'll be able to look at how well our techniques for disentangling these different contributions of the CMB really work. So that's the end of my talk. What I hope you'll take away is that the cosmic microwave background is light that we can detect from the early universe, and that by looking at its fluctuation spectrum, or the patterns of its fluctuations, we can learn a lot about the physics of the early universe, including about dark energy. So with that, I'd just like to thank my fellow presenters, the other student presenters from last year, the demo lab staff, and my advisor in the cosmology group at Michigan for feedback, and my mom and dad for coming to see my talk. So next up is Jim Antonaglia.
My name is James Antonaglia. I'm a second-year graduate student here in physics. My advisor is Professor Sharon Glotzer. The title of my talk is Meddling with Matter, Self-Assembly, and Designing Particles. So I am the alchemy part of our science trilogy this morning. And I chose alchemy as my sort of sci-fi sensationalist term, because really what alchemists do in their labs is they take the fundamental building blocks of a material, like lead, the atoms of lead, they go in with their magic and they manipulate it and turn it into a totally different, more valuable material like gold. And hopefully by the end of the talk, you'll all sort of realize that that's not exactly terribly far off from what we do in our lab in the Glotzer group. So first things first, I would like to talk about building blocks of our materials that we use today. So this is the periodic table of elements. This has basically been our toy box from which we've pulled building blocks and made lots and lots of impactful materials. Most recently, something like silicon and germanium have helped us really improve our lives with materials like semiconductors, like diodes and transistors and solar cells. And all of these things are totally integral to the inner workings of your things like computers, your laptops, and your cell phones and your televisions that sort of define our civilization today. But if those are the materials we live with today, and they're built out of these atoms that we've always been using, what kind of materials and what kind of building blocks will 2030 or 2040 be defined by to make things like cloaking devices or nanorobots or materials that heal themselves when they're damaged or materials that put themselves together, things that we haven't even imagined yet? Are we going to use the same kinds of building blocks, the atoms of the periodic table, or are we going to use something maybe more complex? Because after all you have to do is talk to a 10-year-old who's played with Legos, and they'll tell you, well, if you buy me more cooler Lego sets, then I can build cooler stuff. The more complex building blocks that you have, the more complex, interesting structures that you can make. So the first part of my talk, I'm going to talk about the players in the game, the particles that we make. But what we make things out of is only half the story. We have to assemble them in the right way. So here's a really good example of what I mean. These are two materials that are made of, both are made of carbon, but they have wildly different physical properties. So on the left we have here graphite, which is the same stuff that's in your pencil lead. And on the right we have diamond, which is a really beautiful, hard, durable material. But they're made of the same material, they're made of carbon, and it's all about how they're arranged. Those carbon atoms are arranged. And so I've got the camera on, right? So here we have, oh no, it's out of focus. There we go. It's out of, that's good. So here we have graphite. So it's arranged in sort of sheets like this, but all of the sheets are actually connected by little weak bonds. So obviously not weak here, they're still made of metal. But these sheets have the ability to slide across each other, and that's why pencils glide across a sheet of paper, why they're soft and why they're dull. However, if we look at diamond here, all of the carbon atoms are really well connected. And if you look at one in the middle right here, it has 4 neighbors. All of the carbon atoms have 4 neighbors, and all these bonds are really, really strong. So that's what makes carbon particularly rigid. So even though these two materials are made of the same stuff, they're made of the same building block, they have wildly different physical properties. So the material we build things out of and the way they're arranged have really remarkable impacts on what we use a material for. So the second part of my talk, I'm going to talk about how we assemble things into the right organization. And oftentimes we take, so structure is important or more important than the building block that we use. And oftentimes we take inspiration from biology, because Mother Nature really does this way better than we ever could in a lab, just by trial and error, right? So here on the left, I've got 2 beetles that they're actually fossilized. They're 20 million years old and they've been dug up, and they still retain some of their color. And it's not because that there's pigment or dyes in their wings or their exoskeleton, because that would have degraded over time in the fossilization process. It's actually the structure of their skeleton itself. They're able to take really complex biomolecules, like the things that their bone is made of, and organize it into a very particular way that reflects only particular wavelengths of light. And so they're iridescent, in the same way that the peacock's feather and these really amazing berries that I found a picture of from West Africa, they're totally iridescent like the beetles. So these beetles, that they can take really complex molecules and arrange them in really complex ways and make a material, their exoskeleton, that has totally ridiculous properties that atoms really have a trouble making. So for the last part of my talk, I'm going to give you a few examples of what's been done in the lab to make a material something like this. So first things first, I'll introduce you to the players. These are colloids, or I'll sometimes say nanoparticles, and you can think of them interchangeably. The ones I'm showing up here are just spheres, and we can make them they're also made out of traditional materials. So when I say particles, I really don't mean a fundamental particle, like a neutron or an electron. These are things that we just sort of synthesize in the lab. They can be made of like silica, which is a hard mineral. We can make them out of plastic, like plexiglass, or metal, like gold or platinum. And they're usually in some sort of solution, like oil or water. And these ones are, in particular, spheres, and we've globbed them up into interesting clusters. But we don't have to make them out of spheres. Also, the ones on the left, those are real images of things that have been made in the lab. The ones on the right are obviously just sketches. We can also make, besides spheres, rods and M&Ms and discs. We can make like lots of different kinds of shapes, like squares and triangles and pyramids. We can make branchy, armed, sort of goofy-looking things like spurs or rotors. And we can coat them with whatever kinds of things that we want, like metals or ligands or oils, to make them interact in really particular ways. And on the bottom, you have a scale bar that I've put there. So on the left is 10 nanometers, which is maybe a couple hundred atoms across. And on the right, all the way on the right, we have like 1 or 10 micrometers, which means a couple dozen of these things could fit across the width of your hair. A better example, or a better idea of the sense of scale here is if the particles on the left were the size of a baseball, then the particles on the right would be 3 stories tall. So not only do we have a huge range of creativity in terms of what these particles can look like and how they interact, we can make them attract or repel, we can make them magnetic, we can charge them, we can do whatever we want. We can make them whatever size we want as well. So we have an infinite number of knobs to play with and an infinite number of Lego sets to mess around with. So the challenge now is too much creativity. If you're an experimentalist and you make some of these in the lab, they might be useful, they might not be useful. So this is our job in our lab. We don't synthesize these directly. We actually simulate them in the computer, which is much more useful and much more efficient in terms of exploring this enormous design space, if you will. We have lots and lots of different things to play with. And if we want to ask which of these things would be best suited to make a particular kind of material, it's often best just to run them all in a huge simulation and figure out which one works. In our particular lab, what we like to do is just take one knob, just take one aspect of these particles that we can control, ignore all the others, and see how far we can get with that. So oftentimes, we just change the shape of our particles, give them edges, give them faces, and see what that does. And my work in particular, and the work of a lot of my colleagues, is we play around with particles that look like this. They're called polyhedra. They are all sorts of goofy shapes. There's an infinite number of them, and we can change them in the computer very easily. They have goofy names like icosahedra and truncated dodecahedron and like all this Greek stuff, and I don't really understand. But they're very pretty. We have like a mobile in our lab of just these things hanging around. So these are the kinds of players that we're working with. So these are our building blocks that we use in our computer to make materials. But as I said, structure is very important. So we have the stuff that we're making stuff with. How do we arrange it in the particular way we want? So I'm going to talk about assembly, self-assembly versus regular assembly. So this is a familiar picture from the grocery store. On the left, we have some cantaloupe, and we have some oranges. And they've probably been arranged by a grocer by hand, putting them one next to another. Maybe it took 10, 15, 20 minutes. I don't know. Maybe there's 100 fruit there. No big deal. So this is a structure, an ordered structure made of building blocks, oranges, that you can assemble by hand. But what if you had 1 million oranges or 1 billion oranges? Or to take an extreme example, what if you wanted to assemble an ice cube made of an unreasonable number of water molecules? Even if you could take 1 million water molecules at a time and arrange them into the structure that ice is and lay it down and do this every second, if you do 1 million molecules every second, you still wouldn't be done making your ice cube 10 billion years from now. So to make a material out of really microscopic things by hand, by laying them down, is an impossible task. It's not going to work. So to go from here to here, we need a better sort of solution. And what this grocer doesn't know is that actually this is structure that the oranges are in. They didn't have to be assembled by hand. You could actually assemble this structure from oranges by self-assembly. And what I mean is that they'll actually assemble this structure themselves. So this is a simulation done in our lab by Michael Engel. These are, you can think of them as billiard balls, and we're rattling them around in a box, and they're bouncing off of each other and exploring their space. If they're red, that means that their neighbors are in random positions. But if they're green, that means their neighboring particles are in the same structure that the orange's neighbors are in the grocery store, that they're making a structure. So as we rattle this around, we started with a random mix, and all of a sudden, we get the whole thing to crystallize into an ordered structure. I mean, you wouldn't really want to do this in a grocery store by taking a bunch of oranges in a box, unless you want a bunch of bruised and bleeding oranges. But this is the kind of thing that we're exploring. Another example from the grocery store, if you shop at the People's Food Co-op here in Ann Arbor, you might have seen this in the bulk section. This is wild rice. Up at the top, so a grocer poured this into this large container. And at the top, all the rice is sort of in a disordered mess. But your eye immediately picks out in the center like traces of order, where rice is sort of aligning up with its neighbors. You can see a nice little swooping motion right there in the middle. So I'm going to actually, so this is the same sort of principle. You pour something in a box, rattle it around a bit, and it chooses an order to order into. And I actually have this demonstration here. So I have a plate of rice on top of a dinner platter, and underneath here is a big bass speaker hooked up to a function generator, which is going to make a sound. Yes. It's going to be good. So what the sound is going to do is rattle this plate and hopefully assemble this rice into a similar structure as the rice on here. So. So we have it. We have some domains forming. All the rice has sort of figured out what direction to pick and align up with. I originally wanted to do this with Taylor Swift's "Shake It Off." I tweeted at her to ask her to use the song, and she never got back to me, so I was kind of offended. So we had to settle for this. But this is the kind of self-assembly process that we're looking into. And this is actually very important for technological applications. This is the same process by which the molecules in your liquid crystal displays and your televisions and your computer monitors actually use to order. Those are long, hard molecules that crowded together. They pick an orientation and they manipulate light. So this is important. So to characterize the kind of order that things are set up in, oh, thank you. To characterize the kind of order that things are set up in, we usually talk about something like a crystal lattice. And to talk about a crystal lattice, we can talk about a unit cell. So a crystal, what it is, it's a repeating unit, one by one, laid across itself, according to a set of rules. So this is a checkerboard tile, so black and red. So this is going to be our unit cell. And we have a set of rules by which, if we follow them, we can generate the entire checkerboard layer by layer. So atoms are very, very good at doing this. This is a model of sodium chloride. So the purple atoms are sodium and the green atoms are chlorine. And they're arranged in exactly the same kind of way. So atoms do this very well, so why not our particles? But our particles are way more complicated than atoms, so what kinds of order are they going to choose? So that's what I'm going to get at now, showing you a few examples of things that have been done in our simulation lab and in real experiments. So in our lab, what we can do, we can take a sphere in the computer, and what we can do is shave off a few of its edges, its faces, and give it some edges, and shave those off, and shave those off, and shave those off, until we get to another shape called a tetrahedron, which has 4 faces. And if you've ever played Dungeons and Dragons, that's a 4-sided dice. And not only so we have a sphere and a tetrahedron, but we can generate every shape in between. And this is really important because experimentalists can generate spheres really easily, and they can generate tetrahedra really easily. Well, not really easily, but they can. But they also get a whole slew of shapes in the middle. So it's important to understand how everything in between assembles as well. So here's my little animation. So we generate shapes that look sort of like this. And we want to ask, we throw millions of these in a box in the computer, shake them up, and see what they get. So if we start off with spheres that have just a little bit of faceting on them, it's no surprise that we get something, oh, I didn't change that, something like the order we see in the grocery store in the oranges. Something like, it's called face-centered cubic. It's a crystallography term, I guess I should have changed that. But this is the same structure that we get in the oranges in the grocery store. So they're very spherical still. They still make this structure. We shave off a little more of their faces, and they actually turn into something different, something slightly different. It's called body-centered cubic. We shave off a little bit more, and they actually turn into the same structure that carbon forms. It turns into diamond. And all of these, I mean, maybe you might not be able to see the difference, but if you were staring at them for 40 hours a week for a year, you know the difference. And these are important because, like I said, the structure is very important, as well as the building block, to determine the physical properties of our materials. So maybe these have different, for example, compressions or compression yield stresses and things like these, material properties that are different. And the very interesting thing that we're interested in is once we shave off all of their edges and we turn them into tetrahedra and throw them in a box, they turn into a really bizarre state of matter called a quasicrystal, which sort of challenges our notion of order in crystallography. Oh, and these are Khalid's tetrahedra. I should credit my... and I'm not going to talk about the tetrahedron quasicrystal because it's in 3 dimensions. So I'll talk about a tiling, which is the same kind of quasicrystal. Maybe some of you have seen this. It's called a Penrose tiling. It's actually a popular mosaic pattern. It's very important because it has a lot of order. You can see patterns with your eyes, but it has no repeating cell. It has no black and red checker tile that you can lay down across according to a simple set of rules. You can pick any one of these, and it doesn't take long to realize you can't lay them down next to each other and generate this structure. These are important because they have been made in the lab. They're rather difficult. You need a bunch of different metals melded together at low pressures and high temperatures, and their properties are still being investigated. So, and they're also really bizarre because besides the ones that we know of that we can synthesize in the lab, the only ones that we found naturally occurring in minerals have actually been from meteorites that have fallen from space, because space actually offers a nice environment for these things to form, presumably. There's still studies being done. So these are novel materials, and we don't quite know a lot of their properties. But we made them with Dungeons and Dragons dice in a computer and a box. And so the second example I want to show, to throw back to this slide, these animals exhibit what we call structural color. If you ground up the beetle's exoskeleton into dust, it wouldn't be blue anymore because it's not dye. It's inherent to the beetle's exoskeleton structure. So if you destroy the structure, you destroy the color. And we've done this in the lab. This is Mike Solomon's group, which is one of our experimental collaborators we work very closely with. This is about a centimeter long sample. It's a little dish of liquid with some colloids in it. And right now, it's translucent. This is actually just a digital picture from a regular camera, not a microscope or whatever. But what the colloids are doing, they interact with the solvent and they interact with each other in very, very specific ways. And I won't get into it because actually I don't quite understand because we don't do experiments, we do simulations. So I'm actually quite removed from the real world. But this is an image, so they interact very specifically with electric fields as well. And that's something we can apply externally onto these things. And when they are exposed to an electric field, they actually self-assemble into a structure that exhibits structural color. It turns red when we turn on an electric field. And it's reversible in that we can turn off the electric field and it goes back translucent. So we can do this on and off and on and off. And if we change the size of the colloid particles, we can manipulate the color. We can get yellow and green and blue, all reversibly. So this is a material that has a complex building block that has been assembled into a complex structure and is manipulable. This is like an alchemist's dream. You just get to go in and play with the properties of a material with your hands. So with that, I'd like to conclude. So just my few parting remarks that hopefully you got from this talk, that self-assembly is a really important process involved in making new materials, and it will be really important for making materials for the future. And our group in particular works with drawing the connection between what we build, what the building blocks are, and what the assembled structure is. And we do that through computer simulations. And I want to just hit home that this is not science fiction in that these have been made for the last 20, 30 years. We're making more and more every day, and we're getting more and more creative. And in that sense, we are powerful alchemists, like this wizard here in his amazing laboratory. But as I said, I'm not an experimentalist. I don't know, maybe the experimentalist's lab looked like this, but our lab looks a little bit more like this. And with that, I'd like to send my acknowledgments to my co-presenters, Adam and Jesse, the graduate students who did this last year. They were an immense help. Tim, Jen, and Ben. I'd like to thank my advisor, Sharon Glotzer, and the whole Glotzer group for giving me a lot of data, my parents and family for being here, and the NSF for giving me science dollars. So thank you. And I'd like to present Adam Katcher.
Let me grab this. Okay, so I'm going to be speaking today about quantum teleportation. My name's Adam Katcher. I work in the group of Professor Hui Deng here at the university. So to start out, we're going to put the quantum off, delay that a couple minutes just to ease into it a little bit. So here, this is some familiar things. This is Sir Isaac Newton and the things that he liked to play with in his free time. Toys and planets. He liked both of those things. And so the idea here is that just to start off, we're talking about what's called classical physics, the physics of everyday objects that govern the things in our everyday experience. So here's an example of something that we could all do in our everyday lives, which is to send information, to send a message. So here we have two people, Alice and Bob, and they have some message that they want to transmit from Alice to Bob. So in this case, as you can see, they're separated by some distance on different coasts of the country. And here the message, the information that we want to send is the state of some physical system. So here we have red. Alice has red and blue Legos that she has assembled into some toy, or maybe it's some part of some design that she wants to share. So the idea is that she wants Bob to be able to assemble his objects into the same configuration that she has in her hands. So how do you do that? If you've ever shared an email or sent someone a design for how to construct something, basically you need to figure out. Here we go. We need to figure out what it is that you're sending. So you can basically measure the system. You can check what the color of each Lego is and how they're assembled. And then once you have that information, that completely describes your system, and you can communicate that information and Alice can tell Bob how to arrange all of the Legos with which color in which position. And then he can very easily assemble the state so that he has successfully received the information. This is relatively easy because you can just measure the thing that you're trying to transmit. So just to clarify something, so this basic problem that I'm talking about of transferring information, it's not quite what you might think about from Star Trek, where Star Trek maybe something disappears here and reappears somewhere else. So it's a little different from this, but don't worry, you're still going to get your money's worth because quantum mechanics is plenty weird, even if it doesn't follow science fiction exactly. So just to reiterate how that example worked of sending information from Alice to Bob, we had red Lego bricks, blue Lego bricks, and the way that they worked, kind of our assumption of how these things basically operate, is that, as you know, you can reach in and grab a red Lego from a box, or you can grab a blue one. And unless you're blindfolded or something, you can always grab the one that you want. And there's no real randomness here. This is a very well controlled, building blocks here, red and blue, and there's no real randomness here. So this is kind of the assumption. This might seem very obvious, right? But this is kind of an assumption about how these building blocks work that turns out not to be true in the quantum case. So now we can enter the quantum world. So what this really has to do with, quantum mechanics is the best description for things on physical things on a very small scale. So this is not something we have experience with in our day-to-day lives. This applies to very small objects like electrons, atoms, and photons that are really best seen in a laboratory setting. So it turns out that the way things work on this scale is very different from what we're used to. So one key difference, one key feature of quantum mechanics is that measurements give random results. So unlike the classical Legos where we have red and blue Legos, what we say we have on the quantum level are these objects that are both red and blue at the same time. And so what we use to describe that is we say they're in a superposition of red and blue. So these quantum particles can exist in these strange superposition states. And the consequence of that is that unlike the classical Lego bricks that you could play with, where a blue Lego is always blue, they always have a well-defined color, these quantum particles don't have a well-defined color until you measure them. So you could measure it, you could force it to be either red or blue, but until you do, it's in the superposition. And by measuring it, by forcing it to be either red or blue, you actually destroy this original strange quantum state of being in a superposition of red and blue at the same time. So this is very bizarre. We'll get a handle on how this works as we go on. So here are some examples of different types of superposition states. Just as you can have red Legos or blue Legos in the classical case, you can have different combinations. You could say a mixture, sort of red and blue that can make up different types of superposition states at the quantum level. So here's an example where you have equal outcomes, equal probability of measuring either red or blue. You could have another quantum state that gives you some other likelihood for measuring those two results, depending on how the two outcomes are mixed together in these quantum states. And then in the most general case, you could have a quantum state where you don't even know what it is. So all you know is you have your hands on some quantum system. You've been lucky enough to grab an atom, and you don't know exactly what state it's in, actually. And so you don't know what the different probabilities are if you were to measure it. So the consequence of this weirdness, of these weird superpositions, is that the basic approach we had before to sending information is actually totally ruined. So before the first, let's say now we're not sending a classical design for Legos, but we're sending a quantum state. So the information we want to send is actually this superposition. So the information at the quantum level is really how much of each possibility for red or blue is contained in that quantum particle. So if that's what you're trying to do, if that's the information you're trying to send, then the old approach we had of measuring it actually doesn't work, because if you measure your system, you force it to be either red or blue, and you've destroyed the original state you started with, and now you just have a red or blue quantum particle. So this approach that we did before of just measuring the system and sending information, it doesn't work at all. And in fact, there is a result from the laws of quantum mechanics that says that we can't even possibly copy this state. So these states, measuring these delicate quantum states destroys them. They can't possibly be copied if you have an unknown quantum state. And so we need, if we want to send information on the fundamental level of atoms and quantum particles, we need some new ideas. So we're in trouble here. Quantum mechanics is throwing up these roadblocks. So luckily there is a solution, and it involves things getting even weirder. So the way to solve the problem is to think not just about using one quantum particle at a time, but to think what are the possibilities if you have two quantum particles that exist together. So how does that work? On the quantum level, just as you can have single particles that are in a superposition state, you can also have these weird situations where you can make two quantum particles that are linked together in such a way that we call entangled. So when you have two Lego bricks, they can be either red and blue or blue and red, depending how you stack them. In the quantum case, you can have two Legos where you don't know which one's red or blue, but you know, for example, that they're always opposite. So here's an example. Unlike the classical brick, where if you stack them in a certain way, it'll probably stay that way unless some kid messes them up, or plays with them. Unlike the classical Legos, these quantum bricks, you don't know which one is blue or red. And so you can make these entangled states in such a way that you don't know which is which, but they're guaranteed to be opposite. So this is the key thing about this entanglement, is that it's a link that between two particles that forces them to be, for example, opposite from each other, even though you don't know which color either one of them is. So to get into how some details of that, here we show, again, the key feature of the entanglement is that the other two possible outcomes that you would have, that they would both be the same color, those could be totally prohibited. And that's because you make the particles in such a way that they're guaranteed to be opposite. So to explain a little more about how that works, just as in the classical case, you can combine Legos in different ways, you can also combine pairs of entangled particles in different ways. So for example, here's an example where they're entangled, two quantum particles are entangled so that they're guaranteed to be opposite. And here's a different pair of entangled particles that are guaranteed to be the same color always. So one really weird thing about these correlations, this entanglement, is that it persists over very long distances. So I won't get into this too much except to say that if you, so if we separate them out over a long distance, one to Alice and one to Bob, if Alice measures hers to be red, then because they're guaranteed to be opposite, that immediately forces Bob's particle to be blue. And it turns out that having this kind of interaction over such a long distance leads to some interesting consequences that greatly troubled people like Einstein. So you can check out something called the EPR paradox. So I won't get into this too much except to say that it turns out you cannot use this to transmit any information faster than light. But you can use it actually to do this information transfer at the quantum level. So we're actually going to use this entanglement to achieve the teleportation. So as we saw before, when we try to send information at the quantum level, we run into these roadblocks where we can't measure the state, we can't copy it, so how do we send information? And for a while, no one knew how to do it. So this paper here is from 1993, and they, for the first time, showed how you could send a quantum state, transmit quantum information from one party to another using entanglement. So here is the way to understand this. So there's another way to send just classical information that might seem kind of silly, but it turns out to be useful. So, and this was well explained by Professor from UNSW, Andre Morello, who has some good YouTube videos. So here we have a situation where Alice has a blue Lego, and she wants Bob to also have a blue Lego. That's the information that she's trying to send. She's trying to tell Bob, grab a blue Lego. So one way you could actually do that, it's overly complicated, but one way you could actually do that is to start out with two other Legos of opposite color and randomly distribute them, one to Alice and one to Bob. And if Alice sees that her two Legos are the same color, then she knows that Bob's is red, and so it didn't work. She meant to send a blue Lego, and that's not what happened. So in this case, she can say it didn't work. If in another case, we do the same thing, but now they happen to be randomly distributed in this way. And so if we randomly distribute the two Legos like this, Alice can say, oh, the two Legos I have are opposite. That means the remaining one is blue, and so it worked. And so she can, just by measuring opposite, she can tell Bob it worked. So the key here is that because we start out with two Legos that are opposite color, whenever Alice measures her two Legos to be opposite, that means that the remaining one that Bob has is the same as the color that she put in. So it turns out that this is the only way to get this information transfer to work on the quantum level. So the way that really works for quantum states now is that Alice has some quantum state that she has her hands on. And you use a pair of entangled particles distributed one to Alice and one to Bob. And then Alice, just as we saw before, Alice can just measure, are my two particles the same or opposite color? Every time she sees that they're opposite, she knows that it worked and that Bob's state is now in the same state that she started with. So this is how the quantum teleportation actually works. It's using this entanglement. So now to better understand the dynamics here, we're going to do a quick demo. So yeah, as I said, the emphasis here is that because we start out with two oppositely colored entangled particles, then whenever Alice sees opposite, she knows that it worked. So to demo this, I need 2 volunteers who can quickly join us up here. Some enthusiastic volunteers. Need 2 people. Oh, I see one over here. Perfect. Yes. Can I get you to come up? Yes. Oh, and one here and one here. Perfect. Excellent. Okay, come right up. What's your name?
Same as yours.
Oh, you're also Adam.
Yes.
Oh, excellent. And what's your name?
Will.
Will. Okay. So one of you can send a message, and one of you can receive the information. So who wants to send and who can receive?
I'll send.
Adam will send. Okay, very good. So the way this will work is that if I can get you guys to just stand right up here. So because this is quantum mechanics, you won't get to see what's going on because things are pretty weird on the quantum level. You're not allowed to look. So what we can do is we can just we can have you guys just look up here, and then I'll come right back to you guys. So excellent. So since you're sending a state, you can, yes, you know exactly what to do. Okay, so without looking, and then you can hand it over to me. Thank you. Okay, so Adam is sending a state, and he doesn't know what color it is, and neither does Will. So, but even though neither of them know, you as the audience will get to see what's going on. So here's our, here's the information that we're sending. You know what color that is, but don't say it out loud. And well, the next step, so the first step was to find some volunteer randomly picks a color to send. And he doesn't know what it is. But then the next step is that I have 2 Legos here that are opposite colors from each other. And what I'm going to do is I'm going to distribute them, 1 to each party. So I'll just mix these up here. Okay. So you see how I did that. And now I will go ahead and distribute these to our volunteers. Okay. So here's the sender's stuff. Here you go on the receiving end. Okay. So now the next step here is that on the sending end, can you check whether you can go ahead and open up your box, and now you can look. So can you tell us, are they the same color or opposite?
Opposite color.
They're opposites. Okay. And so that, do you say correct? It worked. Okay. Excellent. And so Will can check. What color did you receive? Blue. And you all know that's the same color that Adam put in at the beginning. So it did actually work. So thank you to our volunteers. Okay, so that's because Adam saw that they were opposite, he knew that it worked, picked up on it very quickly, and Will successfully received the blue Lego. So, and although we did this with classical Legos, I'll just briefly mention that this has actually been done with real quantum particles. Good. So, okay, so here we have an image of 2 islands in the Canary Islands, La Palma and Tenerife. And so what they actually did in this experiment was they had a photon on La Palma, and then they took a pair of photons, distributed 1 to each island, and then on La Palma they measured, are my 2 photons the same or opposite? And every time they saw opposite, just as in our example, they knew that the correct photon state had been teleported, transmitted to the other island 143 kilometers away. So with that, I'll just say thank you to Saturday Morning Physics program, the demo lab for helping us set up, my fellow speakers from last year, my advisor, Professor Hui Deng, and all of you for coming. Thank you.